Hello everyone, welcome to our SIGGRAPH-Asia 2022 talk. I am Chandradeep Pokhria, a first year MS student at the International Institute of Information Technology, Hyderabad, India. I present you Discretization-Agnostic Deep Self-Supervised 3D Surface Parameterization. I co-authored this paper with Shantika Naik, who is also a primary author, Astit Srivastav, an MS student, and Professor Dr. Avinash Sharma. Estimating the UV parameterization of arbitrary 3D surfaces lies at the core of computer graphics and geometry processing domain, with a wide range of applications such as texture mapping, remeshing, shape interpolation, mesh editing, and many more. Formally, surface parameterization is defined as the projection of vertices of the tessellated surfaces, such as polygon mesh, onto a 2D map or a UV plane. Determining this mapping is not trivial and demands a solution with specific properties like conformality, isometricity, and bijectivity. There has been a wide variety of work in the literature to solve this problem. The conventional methods like least square conformal mapping, boundary first flattening, and opt-cuts aim to estimate an object-centric mapping with an iterative optimization process, focusing on minimizing an energy function explicitly constructed to retain the desired properties. However, these methods are non-generalized, may not be robust to noisy meshes, are hard to scale, and require high computation time for large meshes. Our motivation behind neural parameterization comes into view to mitigate these problems. The neural representation for surface parameterization is essential in the generalizability of unseen meshes. We can do a forward pass at inference time just once to get the desired output. This approach is scalable to high resolution meshes and can robust to be noisy meshes. Recently, neural Jacobian fields have been proposed which try to solve some of these issues in a supervised learning fashion. However, with supervised learning, learned parameterization can be as good as the ground truth only. Hence, we lay the foundation of our framework in a self-supervised fashion. We present a novel self-supervised framework for learning the discretization-agnostic surface parameterization of arbitrary 3D objects with both bounded and unbounded surfaces. First, to handle the unbounded surfaces or surfaces with regions of extreme extrinsic curvature, we propose a learning-based partitioning of given surface into multiple bounded patches, which are independently parameterized further to generate a texture atlas. For bounded surfaces, we directly pass them to the surface parameterization module to output the corresponding UV map. We frame the problem of patch extraction as a self-supervised segmentation task that utilizes local features and geodesic laws for estimating patches. We use diffusion-net backbone called PatchNet that assigns each 3D point of the surface to one of the patches. Loss L patch is designed to achieve this task. The loss L cos ensures that the patches formed are as flat as possible. This is imposed by minimizing the cosine similarity of the normals of the vertices belonging to each patch. The loss LGO ensures that the patches formed are not disjoint by minimizing the geodesic distance between each pair of vertices within the patches formed. The patches extracted are further processed individually to obtain their parameterization. For each given input bounded surface, a diffusion-net backbone is used for feature extraction. A forward MLP processes these features along with the input vertex positions to obtain per vertex UV positions. We impose L area and L angle laws, ensuring that the angle and area of the projected UV triangles and the input triangles are the same. L-ISO minimizes the difference between the geodesic distance on the 3D surface and the Euclidean distance in the UV space. Another backward MLP maps the UV vertices back to 3D, and L cycle loss is imposed between the reconstructed and input 3D surfaces. This cycle consistency loss is used to ensure bijectivity. Here, we show the results of our framework for the hemisphere, which is a bounded surface. We use quasi-conformal error, also known as QCE, as a metric to plot the conformal distortion in both 2D and 3D. Red values correspond to extreme distortion, while blue values correspond to no distortion. Similarly, we show results for the phase. Notice that with the increase in iterations, the conformal distortion is reduced by a significant amount. The reconstructed point clouds are the prediction of the backward MLP. We notice that the quality of the reconstructed point cloud has a high correlation with the distortion in parameterization. Now we show results on unbounded surfaces. Remember that for unbounded surfaces, we use PatchNet for generating seams and partitioning the mesh into multiple patches. Once patches are generated, we can feed them to the surface parameterization module to get the file UV map. Here we show the QCE plot on the 3D surface of the duck, and the right to it is the 3D textured mesh. These are the convergence visualizations of our network for Sphere. An important feature of our framework is discretization-agnostic learning. During training time, the network is trained on a low-resolution mesh in a self-supervised manner, while during inference, the network can generalize to meshes of any resolution of the training sample. Notice that the inference for high-resolution meshes can be made within seconds with no significant increase in the errors. Now, we show the category-specific generalization capability of our network on the SHREC dataset. The network is trained on 16 samples and tested for 4 unseen samples. We show the qualitative comparison of our method with boundary first flattening and opt-cuts on the SHREC dataset. The first two categories are BERT and pliers from SHREC dataset. Remember that these are the generalized results of our framework, while other methods are object-centric. The next two categories are armadillo and spot. Here, we also train in an object-centric manner, and our results are on par with other methods. We compare our method quantitatively with boundary first flattening and opt-cuts on quasi-conformal error and area scaling error, and show that our method is on par with existing methods. We also compare computation time and show that our inference time is faster than existing methods for high-resolution meshes. We do a detailed analysis of our framework on various fronts. For PatchNet, geodesic loss along with normal loss helps in forming continuous local patches. Without geodesic loss, we can see the formation of disjoint patches across the mesh whose normals are directed in the same direction. For PatchNet, we can increase the number of patches up to any amount, and increasing the number of patches reduces the overall quasi-conformal error and area scaling error up to a limit. We argue that when the patches are very flat, the surface parameterization module does not find many clues for self-supervised learning. Here we show the effect of different loss functions on the conformal distortion for the surface parameterization module. When all losses are plugged together, surface parameterization module performs best. Diffusion blocks play a significant role in the convergence as well as the generalization of our network. In particular, global diffusion embeddings carry more information about the global shape of the object and hence performs better. We can see that when per vertex diffusion embeddings are used instead of global ones, the distortion significantly increases. Though our method has brought out the proof of concept to do neural parameterization in a self-supervised manner, our method has several limitations. Right now, we don't focus on resolving the overlaps or ensuring the bisectivity of the learned mapping, which is an interesting future direction for us. Another limitation is that the formulation of PatchNet does not guarantee to give continuous patches even if we apply geodesic loss. One more limitation of the surface parameterization module is that it can't handle very severe protrusions even if the surface is bounded, which can be solved by considering the extrinsic curvature of the mesh. Finally, we acknowledge anonymous reviewers for their constructive comments, Keenan Crane for open sourcing the Spot and Bob mesh, Dhawal Sirikonda for helping us with the visualization of the QCE error metric. Thank you.